Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. The starting alcohol is H2C is equal to CH, CH2CH2C, or CH2CH3, where the carbon bearing OH also bears an ethyl group and is connected to the butynyl chain, CH2CH2CH is equal to CH2. This is a tertiary allylic alcohol. The OH is on a tertiary carbon, but the double bond is terminal at C1, C2 of the chain, i.e., homoallylic position relative to the OH carbon. Moving on to the next step. TSOH is an acid catalyst. Acetone reacts with the tertiary alcohol under acid catalysis. Since the alcohol is tertiary and acetone is a ketone, this forms a mixed ketal, actually a tertiary alkyl vinyl ether, or more precisely a tertiary ether by acid-catalyzed reaction. More precisely, under TSOH, the tertiary alcohol reacts with acetone to form a 2,2-dimethyl 1,3-dioxolane type protection, or simply forms a tertiary alkyl isopropylidene ketal. The product, A, is the isopropylidene ether. The OH is protected as OC, CH3, 2. But since it is a monoalcohol, not a diol, it forms a mixed tertiary ether, ROC2, or via the enol ether mechanism, ROC, CH3, is equal to CH2. Actually, with TSOH and acetone, a tertiary alcohol undergoes acid-catalyzed esterification with the enol form of acetone to give ROC, CH3, is equal to CH2, isopropyl ether. So, A is equal to H to C is equal to CH, CH2, CH2C, at CH2O, C, CH3, is equal to CH2. Wait, the OH is on the quaternary carbon. Actually, there is only one OH. Under acid with acetone, the reaction of a tertiary alcohol with acetone TSOH gives the tertalkyl isopropyl ether via an SN1 type mechanism or via protonation of acetone enol. So, A is equal to H to C is equal to CH, CH2, CH2, at OCME is equal to CH2, i.e., the terminal alkene is still present plus a new isopropyl ether. Moving on to the next step. Ozonolysis of A with O3, CH3, 2S, reductive workup. Ozonolysis cleaves C is equal to C double bonds to give carbonyl compounds. Compound A contains two double bonds, I. The terminal alkene H to C is equal to CH from the original starting material, and 2. The isopropyl ether double bond OC, CH3, is equal to CH2. Ozonolysis of H to C is equal to CH terminal, monosubstituted, gives HCHO, formaldehyde, which is the HCHO shown in the product, plus an aldehyde at the other carbon. Ozonolysis of OC, CH3, is equal to CH2 gives HCHO, from is equal to CH2 end, plus an ester ketal fragment, OC, CH3, is equal to O, which is actually OC, is equal to O, CH3, methyl ester. Wait, ozonolysis of a vinyl ether ROCR is equal to CH2 gives ROC, is equal to O, R, and ester, plus HCHO. So the isopropyl ether, OC, CH3, is equal to CH2 upon ozonolysis gives OC, is equal to O, CH3. But that gives an ester, not matching option A. Let me reconsider. With TSOH and excess acetone, to methoxypropene equivalent, a tertiary alcohol can form a cyclic protecting group if there are two OH groups, but here there is only one. Alternatively, the reaction could form a hemiketal or the tertiary carbocation could rearrange. More likely, TSOH catalyzes the reaction of the terminal alkene, allyl system, with acetone via a Prince-type cyclization, or the alcohol attacks acetone to give a mixed ketal on both the OH and the allylic system. Actually, rereading, the molecule has a terminal alkene and a tertiary OH separated by two CH2 groups. Under TSOH acetone, a Prince-type cyclization could occur, forming a cyclic ketal where the alkene and the alcohol react with acetone. This would give a 6-membered ring, 1,3-dioxane derivative, or similar. The Prince cyclization of a homoallyl alcohol with a carbonyl compound under acid gives a tetrahydropyrin. Here, the OH and terminal alkene are 1,4 related, or on C5 alkene on C1, C2 with C3, C4 as CH2CH2, so a 6-membered ring could form. Under Prince conditions with acetone, A would be a 1,3-dioxane cyclic acetyl, incorporating the two oxygens from acetone and the tethered alcohol. Actually, the Prince reaction of a homoallyl alcohol with ketone acid gives a 1,3-dioxane. The product, A, would be a cyclic 1,3-dioxane with the acetone-derived dimethyl substitution at C2 and the ethyl group and CH dependent from the ring carbons. And for the final step, the ozonolysis of A gives B plus HCHO. HCHO comes from a terminal is equal to CH2. Looking at option A, it shows an aldehyde HC is equal to O, CH2, CH2, at CH2O, CMe2, O, CMe2. This structure has the quaternary carbon bearing at A, CH2O, CMe2 group and an O, CMe2 group, a hemiketal ether from acetone. This is consistent with the original terminal alkene H to C is equal to CH was cleaved by ozonolysis to give HCHO plus the chain aldehyde OHC, CH2, CH2, at. The acetone-derived protecting group on the tertiary OH is OC, CH3, 2, which upon ozonolysis of the isopropanol ether gives the ketal fragment. Actually, if A is the isopropanol ether ROC, CH3 is equal to CH2, ozonolysis gives ROC is equal to O, CH3 ester, which does not match A. But option A shows OC, CH3 to intact, suggesting the ketal oxygen is not from ozonolysis of the protecting group double bond but rather the protecting group double bond is the one that gives HCHO. Ozonolysis of ROC, CH3 is equal to CH2, the is equal to CH2 and gives HCHO, and the ROC, CH3 is equal to and gives ROC is equal to O, CH3, an ester. This gives option C, pattern, format like, if the other alkene is also cleaved, but option A shows O, CMe2, dimethyl substituted carbon still attached to O without a carbonyl. Alternative, if A is the THP, Prince product, a cyclic 1,3-dioxane with no remaining double bond, then there is no double bond to cleave. So A must retain a double bond. Most likely interpretation, TSOH acetone converts the tertiary OH to O, CMe2O, hemiketal, unstable, or more practically the reaction of the tertiary alcohol with 2-methoxypropene, formed from acetone TSOH, gives ROC, CH3, is equal to CH2, the isopropanol ether. Then ozonolysis of both double bonds, terminal alkene H to C is equal to CH, HCHO plus OHC, the stated HCHO, and isopropanol ether OC, CH3, is equal to CH2 OC, is equal to O, CH3 plus HCHO. But the question says only HCHO is the coproduct, B plus HCHO, implying one equivalent of HCHO total. This means only one double bond is cleaved, or both give HCHO but only one is shown separately. Actually rereading B plus HCHO, So HCHO is one fragment and B is the other. With two double bonds cleaved, terminal alkene H to C is equal to CH, HCHO plus CHO incorporated in B, and OC, CH3 is equal to CH to HCHO plus OC is equal to O, CH3 ester in B. This would give B as OHC, CH2, CH2C at O COH3 with a CH2 fragment. This is getting complex. Let me try a cleaner approach, looking at option A directly. Option A is OHC, CH2, CH2C at CH2O CNE2. Specifically CH2O C, CH3, 2 as a pendant group, and OC, CH3, 2 as the main chain ether. The structure has CNE2 connected to two oxygens, one from the CH2O and one from the CO on the quaternary carbon, making it a cyclic acetyl fragment, neopentyl glycol ketyl type. Wait, looking at structure A, again, the quaternary carbon has at CH2O CNE2, O CNE2, and CH to CH2 CHO. The CNE2 is bonded to both an O from CH2O and an O from the direct CO linkage. So CNE2 is part of a cyclic structure, C, quaternary, O CNE2O CH2C, quaternary, forming a 5-membered ring, 1,3-dioxylane. So, A is a 1,3-dioxylane, cyclic acetyl, formed between the tertiary O and the CH2O. But there's no CH2O in the starting material. Wait, perhaps the starting material I'm reading is wrong. Let me reread. H to C is equal to CH, CH2, CH2C, or CH2, CH3, with also a CH2O group. The structure shows C-bearing O, with CH2, CH3 as one substituent, and the main chain connects to CH2, CH2, CH is equal to CH2. There appear to be two substituents on the C, CH2, CH3, and from the drawing possibly also a CH2O, making it a diol. No, looking again, the structure is H to C is equal to CH, CH2, CH2C, or CH to CH3, where the vertical bar above C means there's something above. Looking at the image description again, the CO has a vertical bar above it indicating another substituent. Actually, the structure written is H to C is equal to CH, CH2, CH2C, or where C also has CH2, CH3 below. The vertical bar above CO might mean the C is connected to the chain above, making it the chain is .CH2C or dash, with CH to CH3 as a branch below and the alkene chain to the left. So the compound is pent-4N1-ol type with branching specifically 2-ethylpent-4N1-ol. No. Let me just accept the alcohol is a tertiary alcohol with one O, one ethyl group, and a butanol chain, CH to CH to CH is equal to CH2. Molecular formula contribution, the C-bearing O has O, CH to CH3, CH2 to CH is equal to CH2, and one more group, since it needs 4 bonds. Looking at the image, there's a vertical bond above CO suggesting the chain continues above, but the leftmost part H to C is equal to CH, CH2, CH2 is the chain. So it's quaternary C, O, at CH to CH to CH is equal to CH2, and the vertical bar above might just be the bond to O shown differently. If it's truly tertiary, 3 C substituents plus O, the fourth substituent must be H, secondary, or another carbon group. Given the image shows vertical bar above CO, perhaps there's a methyl group above giving C, or CH3, at CH to CH to CH is equal to CH2, a quaternary alcohol, no H on the O-bearing carbon. That makes it truly tertiary. Actually, the most consistent reading, the starting material is 2-ethyl 2-methylpent-4-N-1-ol. No. Let me just accept the starting material as drawn with a tertiary C bearing of CH to CH3, CH to CH to CH is equal to CH2, and possibly a CH2 based on how option A makes sense. If the starting material has both an OH and a CH2 group, i.e., it's a diol, CH2C, OH at CH to CH to CH is equal to CH2, then with acetone TSOH it forms a cyclic 1,3-dioxylane, 5-membered cyclic acetyl, protecting the diol. This gives A is equal to 2,2-dimethyl, 1,3-dioxylane with the butanil and ethyl substituents on C4 of the dioxylane, plus the terminal alkene intact. Ozonolysis of the terminal H to C is equal to CH, then gives HCHO plus OHC fragment, where the CHO-containing fragment is B is equal to OHC, CH2, CH2C, at CH2O, CMe2O, as a cyclic ketal. This matches option A perfectly. The dioxylane ring is drawn open in A as CH2O, CMe2O, with CMe2 bridging to oxygens. The aldehyde comes from ozonolysis of the terminal alkene. H to C is equal to CH, HCHO plus CHO, and the cyclic acetyl, dioxylane, is preserved. HCHO is the coproduct from the is equal to CH2 end. Therefore, the starting material must be a 1,2-diol, or at least have a CH2 group alongside the tertiary of H to C is equal to CH, CH2, CH2C, or at CH2 a tertiary diol type, 2-ethyl, 4-pentan, 1,2-diol. Actually 2-ethylpent, 4-Na, 1,2-diol or similar. This diol reacts with acetone TSOH to give the cyclic acetyl, 1,3-dioxylane, compound A. Ozonolysis of the terminal alkene in A gives HCHO plus the aldehyde B. Option A shows B correctly as the aldehyde with the intact 1,3-dioxylane drawn in open form showing both CO bonds. Verification against other options. B shows a cyclic peroxide 1,2-dioxylane, which would require different reaction conditions and doesn't arise from standard ozonolysis ketal chemistry. C shows a formate ester HOC is equal to O, which would come from formic acid, not expected here. D has only one CH2 between the aldehyde and the dioxylane carbon, but the starting material has two CH2 groups, CH to CH2, between the terminal alkene and the quaternary carbon, so after ozonolysis there should be two CH2 groups matching A, not D. Therefore, the correct answer is A. Therefore, the correct answer is option A.